Hello, this is Mrs. Ross, and this is lesson 4.1, polynomial functions. There's a lot of vocab in this lesson, so just hang with me as we get through it. Some of it we've seen before, such as a power function. We saw that in our last lesson. This is a monomial function, monomial meaning one term, in the form of this. It can be 3 times x squared, negative 2 times x to the fifth, whatever. That's a power function. A polynomial function, this literally means many, and this is terms. So it has many terms. It says it can either be a monomial power function, or it can be written as the sum or difference of power functions. When it talks about that, it's talking about like 2x squared plus 3x minus 12, or something to that effect. That's a polynomial, okay? The degree of a polynomial is the value of the highest or largest exponent. So for my example, the degree would be 2 because that's the highest exponent. The leading coefficient is the coefficient or the number in front of the term with the highest degree. So again, in my example, my leading coefficient would be 2 because that's what's in front of x squared. And then lastly, a standard form. So standard form begins with the leading term. So begins with the whatever the largest is, and the other terms are written in descending order. Now, if I wrote this, negative 12 plus 2x squared plus 3x, this is not standard form. Okay. All right, so here's some examples. Okay, and what they want is, it says identify the leading term, the leading coefficient, the degree, and if it's in standard form. Okay, so let's look at this one. The leading term is 4x squared because it has the largest. The leading coefficient is 4. That's the number in front of the variable. The degree is going to be 2. That's the largest exponent we have. And it is in standard form because it's descending. So we have x squared, we have x to the 1 basically, and then no x's. Okay. Let's pick a different color and do the same thing here. Leading term, leading coefficient, degree, in standard form. If you want, I can't write and speak in the thing. Okay. If you want, you can pause the video right here, see if you can write these things down and get them correct. But the leading term for us is negative 3x cubed. Even though it's not in the front, it's the one with the largest exponent. And the leading coefficient is negative 3. The degree is 3 because it's x cubed. And this is not in standard, this is in standard form. This is not in standard form. Okay, so the leading term test. The leading term can be used to determine end behavior. End behavior, yeah, this is not helpful at all. Go to the next slide. Okay, aha, this is this. So this page and the next page are hugely helpful. I went back to these when I was doing the practice and all of that stuff. So there's even degree functions. These are your x squared, x to the 4th, x to the 6th. Even degree functions, okay, when the leading term is positive. Okay, so this could be 3x squared, 1/2 x to the 4th, 8x to the 6th, whatever. These are just examples. This is what the graph is going to look like roughly. It's going to rise on both ends, and it's going to have these end behaviors. I thought we were done with those. We are not. Sad face. Okay. If, let me get another color. I want green. Okay. If the leading term is negative, so that means negative 3x squared, negative 1/2 x to the 4th, negative 8x to the 6th, then this is the end behavior, and it will fall on both sides. Okay. So this is if it's an even degree function. The next page is if it's an odd degree function. Okay, so this is like x cubed, x to the 5th, x to the 7th. Okay, odd degree functions. If the leading term is positive, so 3x cubed, 4x to the 5th, 1/3 x to the 7th, that's gross. Then this is our end behavior, and it's going to rise to the right and fall to the left. Okay, this is kind of a rough what it's going to look like. If the leading term is negative, so we have negative 3x cubed, or negative 4x to the 5th, or negative 1/3 x to the 7th, this is our end behavior, and it's going to fall to the right and rise to the left. It flips. These two slides, this one and the one right before it, I don't know, just put stars or hearts or unicorns on them so that you know that you're going to come back to these. Example. Sorry, got to flip all my pages. Here's we go. So it says, using the leading term test, determine the end behavior of the graph. Okay, so my leading term is 8x cubed. My leading coefficient is 8. And my degree is 3. Okay, all from right here. Okay, so if I look at the notes, we know that this is an odd degree function. Right, because we have x cubed. And the leading coefficient is positive. So if I go back and I look at it's an odd degree function, leading coefficient is positive, that's right here. So this is my end behavior right here. Okay, so that's exactly what I'm going to look for or write over here. So as f of x goes to infinity, x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. It rises to the right and falls to the left. Okay. Okay. Turning points and extrema. Oh wait, we're not at extrema yet. So turning points is just when it goes from increasing to decreasing. So we have a turning point here, and we've got a couple of them here. What's interesting is, well, I think it's on the next page, the interesting thing. So the graph of a polynomial function degree n can have no more than n minus 1 turning points. For example, if I have, if 4x to the 4th is that's the degree of my polynomial, I can only have the maximum of 3 turning points. If I have like 1/2 x squared, I can only have a max of 1 turning point. Okay, so these are my max possible. Doesn't mean you will have 3. It means that's the max you could have. And now we talk about extrema, which sounds like a superhero to me, but not so much. These are places on the graph where it reaches a high or a low. Okay, so there's a global max and global min, and local max and local min. This makes more sense, I think, when we look at graphs. So, and then this is gross. This doesn't make any sense at all. I copied and pasted because it was in blue and looked special. Let's actually do the work. Okie dokie. Okay. All right, so one thing I noticed is when they started talking about local max and local min and global max and global min, they start using randomly, they start using the quadrants, which is kind of cool because we're using them in physics right now. Yay, go us. Okay. So what we have is this is going to be a local. This is a local min. This is a global min. Meaning it's never going to get less, it's never going to go lower than this. Okay? Because both sides are going up, there's not a global max because it goes on forever up. Okay, let me change colors because that makes me happy. Okay, 1, 2, 3. I'm just naming my quadrants before we get, because that's what's down here. Okay. Okay, so I know that we've got a inflection point there, there, and there. Okay, so we have a global max here. That is as high as this is going to get. It's not going to get any higher because both of the ends are decreasing. Okay, and then we have a local min, and we have a local max. Local max, okay. All right, let's do a couple more. Okay, and let's change colors. I want orange. Yeah, okay. So we've got several different inflection points on this one. What we don't have is we have no global extrema, no global max, no global min, because this is going to go on forever and this is going to go on forever. So all of these are going to be local. So these two are local maxes and these two are local mins, minima. The minima, let's do green. Okay, and then this is the last example we have for these. And wherever it changes direction, I just put little dots because that reminds me. And again, this has no global extrema because it goes up forever on that side and it goes down forever on this side. So we have two local mins and we have two local maxes. The page. It's going to have to be two parts. And extreme value theorem. If a function is continuous on a closed loop, then f has a maximum of min on the interval. Well, probably if you close it. I mean, okay, so this is what I did for this one. Here's the example. It's super small. I graphed this in Desmos. Okay. And when x was 1, y was equal to negative 10.67. When x was 3, these were some of the extrema. Y was 0. When x was 0, because we're going to try this right here, right? Y was negative 3. And when x was 4, y was equal to 30.33. So this was the max. This was the min. Nope, lie. Lies. All lies. Hold on. I chose the wrong one. Not all lies. Just partial. Oh, I don't want the highlighter. This is the min, I believe. The min is 0. That's what I know. Okay, this is going to end up being a part 1 and part 2. So on this page, here's what we need to do. Okay. I'm going to write, we're trying to find leading coefficient, degree, and leading term, and if it's in standard form. I'm going to write whatever the function is, leading term, leading coefficient, my handwriting is just atrocious, degree, and standard form. We're going to do this for each of these 4. So my suggestion is like to pause the video and do A, B, C, D and have these, okay? And then maybe even try them and come back and check them against my video, okay? I think we have enough time to at least do the first one. So let's see, the leading term is going to be negative x squared. The leading coefficient is negative 1 because remember we have an invisible 1 in front of this. The degree is 2 and it is not in standard form because the x squared is not in front. Let's see if we can do this a second one. So if I did b, b is 6x cubed minus 3x plus 9. My leading term is 6x cubed. Leading coefficient is 6. Degree is 3 because it's x third. And this is in standard form. Okay, I'm going to do C and D on the next video.